for joining us today for Behind the Scenes of ChatGPT with Jay Modi. Jay is a student at McMaster who just completed his internship at Cohere, where he worked on training machine learning models similar to ChatGPT. Welcome.
Hi, everyone. Thanks for the intro, Trinity. Yeah, so let me just share my screen. Cool. Can everyone see my screen?
Yep.
Cool. I'm just gonna move the. Can you see me as well, or
Yeah.
like on the side? Should I leave that there, or should I put it somewhere else?
Oh, it's just like the Zoom window, so we can move
Okay,
it if
I'll
we
put it
want.
somewhere else. Okay, cool. All right, welcome everyone, and today we're going to be talking about ChatGPT. Now, I'm sure. Oh, sorry, we already introduced myself. So I'm sure by now that we've all heard and probably have used ChatGPT. But if you're unaware, I'm just going to give a quick demo of what ChatGPT is. So ChatGPT is a language model. It's an AI system created by OpenAI that you can essentially talk to, right? And you can ask it to do a bunch of things. For example, they have some examples here. Let's do explain quantum computing in simple terms, right? And then you can talk to the model, and in a second, after it loads, it'll start talking to you, right? Quantum computing is a new kind of computing technology that uses principles of quantum mechanics, a branch of physics that studies the behavior of matter, energy at the smallest scales. Yeah, so it's a pretty intelligent AI, and you can go back and forth with it. For example, like you can ask it some new questions, like give me gift ideas for a 10-year-old, right? And it'll brainstorm some ideas, right? And you can even like add upon that and be like, the gift is for a boy, he likes cars, right? And then so you can get more specific with your like suggestions, right? So it uses that previous context in the chat to, expand further. And it's a quite intelligent system. You can use it for a bunch of things. You can even ask it to program. Can you write me Python code for the Fibonacci sequence? And here you go. There's some Python code for the Fibonacci sequence. You can even make it more efficient. Let's stop. Make it more efficient, and then it'll make it more efficient. There you go. So pretty impressive stuff. And so today, my goal with this presentation is to do a high-level introduction, and it's going to be based off a blog post I wrote called GPT in 60 Lines of NumPy. And my goal is at the end of this presentation, those 60 lines that I'm talking about, this is those 60 lines. I'm basically going to hopefully make you understand these last 15 here that are pretty critical. And you don't have to understand neural networks or AI or any of that stuff to really grasp these last couple of lines. And that's kind of my goal, and that's kind of where we're headed in the next 45 minutes. Yeah, and feel free to check out like the full blog post as well. I mean, it's really long, but it's also a super in-depth kind of coverage of the entire thing, and it goes through all 60 lines and derives like how do you actually code a GPT model. Yeah, so yeah. Now, before we actually do get to GPTs and all that good stuff, we do have to take a little bit of a detour into AI, deep learning, machine learning, and all those terms, because those are things that we need to understand before we can move on to GPTs themselves. Okay, so we're going to break down kind of these three concepts: artificial intelligence, machine learning, and deep learning. So at the top kind of superset of everything is kind of artificial intelligence, right? So artificial intelligence is just like, problems and systems that solve complex tasks that require sort of intelligence, right? So for example, the picture here is object segmentation and detection. So it's just an AI model that looks at a picture and determines, there's a car, there's a person here, and whatever. There are other examples of AI systems like facial recognition, like on your iPhone, time series forecasting, like stock prediction, natural language processing, so like sentiment analysis, figuring out if someone is saying something positive about a movie or negative about a movie or neutral, right? And then, YouTube's recommendation algorithm is an AI. You can call it an AI. And there's lots of other examples. Now, it is a little bit ambiguous, though, the term, like what is an AI, what's not an AI. one point, chess used to be considered like the pinnacle of human intelligence. And if, a computer could beat, humans at chess, that was considered like the peak of artificial intelligence. Nowadays, we have chess engines and we don't even call them AIs. We just call them chess engines, right? Some people are just like, oh, it's just brute force search. And there's like Larry Tesler has this theorem that's like, AI is whatever hasn't been done yet. So, some hard problem is considered AI and then, people solve it and then it's no longer AI. To complicate this further, some people also use like AI to like, mean like artificial general intelligence, like HAL 9000 from A Space Odyssey or Sunny from iRobot. But in general, we can just kind of think of AI as like any task or system that solves a problem that would usually require like intelligence. Now, a subset of AI would be machine learning. We can tackle a lot of AI problems through machine learning. And to understand what machine learning is, we first have to understand how regular like algorithms work. So a regular algorithm, we have a problem. We give it to a programmer, and then the programmer solves the problem with an algorithm, right? So in this case, the example I'm giving is sorting a list of numbers. We give that to the programmer. The programmer comes up with the algorithm merge sort. We then feed the algorithm an input. So in this case, an unsorted list, and then it solves the problem. It gives us a sorted list. Machine learning algorithms, on the other hand, don't work like that. Instead, we give the problem to the programmer, and the programmer, instead of coming up with a direct solution, they come up with a training algorithm, machine learning training algorithm. Now, in turn, we feed input-output examples, so data, to that training algorithm, and then the training algorithm itself comes up with the final, what we call inference algorithm that gives us the transformation from our input to output and solves our problem. So we're not directly solving the problem. We're solving the problem through a machine learning algorithm paired with data. So in this case, the example I'm giving is classifying pictures of dogs and cats. The algorithm of choice here is a neural network. And then we show the neural network a bunch of pictures of labeled pictures of dogs and cats. Keyword there is labeled. They have to be pictures that have the correct label to them. So if it's a picture of a dog, it needs to be annotated by a human saying that's a dog, right? And then, of course, once we train the neural network, then we come up with a trained neural network, which is your inference algorithm. And then we can use that to infinitely classify pictures of dogs, like that cute dog in the bottom left. Yeah. And also, we could actually also use neural networks to solve the problem of sorting a list, but that's kind of not the point. ML algorithms are specifically good for problems that are, hard for a computer to solve, but easy for a human to solve. They're better at like abstract tasks rather than like concrete solvable problems like sorting a list. Now, even one level down from machine learning is deep learning, which is a type of machine learning algorithm specifically revolving around neural networks. Okay, so what the hell is a neural network? So this is just kind of a visualization of what a neural network looks like. It's basically a series of what we call artificial neurons composed in these layers. So on the left side, we have the input layer where we feed the model input data, so just numbers, and we'll see an example of that later. In the middle, we have these hidden layers, and then the output layer is whatever we want to predict, right? Now, the fact that we have hidden layers and we could have a really deep network in terms of like the number of layers is why we get the name deep in deep learning. It's referencing like how we can make a neural network really deep by just adding more layers. We can also make the neural network wider by adding more neurons, but the deep in deep learning refers to that. So as an example, we can create a neural network where we give it as input age, weight, and shoe size, and we can have it predict the height, right? And in the input, like age, we might put like 37, and weight, you might put like 150 pounds, shoe size, you might put size 12, and then output would just be a number for your height in like, let's say centimeters. Now, these little circles in the middle, in the hidden layer, we call them neurons, artificial neurons. And all they really are, it just holds a number. So in this case, I'm just giving an example of 1.23. Now, the lines that connect to neurons are what we call weights or parameters. And they also just hold a number. In this case, I gave it negative 0.44. Now, the way we calculate the value of a neuron is we take the value of the previous neuron. So for example, I'm just showing one specific neuron example here. We can compute Y1 by taking X1, multiplying it by the weight, taking X2, multiplying it by its weight, and then X3 multiplying by its weight 3. So you can see that at the bottom here, W1 times X1, W2 times X2, W3 times X3, and you sum them all together, and then you put them through some kind of activation function. So what the hell is an activation function? It's just some kind of non-linear function. It doesn't really matter. Just know that essentially it's the weighted sum of all your previous neurons, which is where the word weight comes from. Yeah, and so if you do that throughout the entire network, then you can basically go from layer to layer, and your neurons are passing on information, and you get to your output. So for a more concrete example, let's take a look at classifying like a handwritten digit. So here we have an image of a 3, a 28 by 28 black and white image, and you can see each pixel is represented as a number between 0 and 1, 0 meaning black, 1 meaning white, and then everything in between would be like a different hue of gray. And we can take that 28 by 28 image, we can flatten it out into a single list of numbers. So 28 by times 28 is 784. So that's our input layer. And then as the information propagates through the network, we go from our input to, you can see the middle layers are getting activated, and then finally our output. And in this case, the color, the stronger the green color, the more we say that, like, the higher the value is. And then at the end, we see the highest value is associated with 7. And so that's the network's prediction. It's predicting that 7 is the number in the image. Yeah. And basically, one thing that I kind of skipped over is, well, how do we choose like the value of what the weights should be, right? Well, first of all, when we initially start with a neural network, they're initialized randomly. But then they go through a training process where we show the neural network examples. Remember, from like the machine learning example, it goes through a training process. And then through the training process, we come up with an optimal set of weights. And I'll show you an example here. So this is a really great kind of playground, playground.tensorflow.org, where you can basically watch a neural network be trained. So here we have a simple neural network with 2 inputs, an X and a Y. So we can plot it on the right here. And then the output is just a single probability. I think it's like the probability that either it's blue, like this data point is blue or orange. And then in the middle, we have 2 hidden layers, one with 4 neurons, one with 2 neurons. And when you can see initially randomly, it's hard to see with the faint color, but our neural network is predicting that all of this area is blue and all of this area is orange. But as we start to learn and we hit the run button, we can see that it slowly learns the correct classification of things. Of course, we can play around. If we reduce just to 1 layer, you'll see that it has a much more difficult time learning. And then we can, remove the neurons completely. And you can see that when we have just a single layer neural network, it doesn't learn anything. So you do need to have like kind of like a deep and a bit of a wide network. And also, the more complex your task, so let's say this task, you're going to need a more complex neural network with even more layers. Let's say ReLU, and it should learn over time. It should, in theory, if I, let's say, reduce this down, let's just try it. Yeah, it should, I think over time, it'll learn a little bit better and better, but give it some time. And yeah, you can start to see that it's starting to learn how to classify it like more complex things. Yeah, so that's just kind of an example of how neural networks work. And you can see that, when we start initially, see the value of this weight is negative 0.24. As we start learning, you can see that it's being updated slowly and slowly. So it went from negative 0.24 to negative 0.334, right? So slowly over time, as we train the model, we come up with an optimal set of weights. Okay, so that's what a neural network is. Any questions so far? Let's see, there's one message in the chat. Oh yeah, I'm just about messages. Okay, cool. So I'm gonna move on, no questions so far. Now, why use deep learning, aka neural networks, over other kinds of ML algorithms? Well, the key advantage to neural networks is that as you show it more data, you can scale the model, make it bigger, more layers, more neurons, and it'll just keep getting better and better. Unlike older machine learning algorithms, like more conventional ones, there's kind of a limit to how much data you can show it, and it just will stop improving. And that is why recently, in the last 10 years, neural networks and deep learning has kind of blown up, right? You hear about it all the time, ChatGPT is a neural network. Facial recognition is a neural network, and all that good stuff. And these algorithms are not new. Like the neural network is invented in the 1950s, like the artificial neural network. The algorithms we use to train them date all the way back to the 1850s. But what's different is we didn't have enough data and fast computers as we do today. And that's thanks to the internet for all the data and Moore's law, just computers getting faster and faster, because training these networks takes time. And so just in the last decade, we've had both, and that's kind of why you're seeing neural networks kind of pop up everywhere. And last thing I'll quickly mention is that we looked at a very simple neural network. We call them, the ones that we saw were fully connected because each layer was fully connected with each other. When in reality, there's lots of different kinds of architectures and there's kind of different ways to connect neurons and everything. And there's like more hidden complexities. So there are different architectures as well, but the one that we saw was like the most simple, basic, fully connected neural network that kind of just demonstrates the principles. Okay, so that was a bit of a long detour, but yeah, so that was kind of like an introduction to just AI, ML, and deep learning. I'll quickly pause again here if anybody has any questions to clarify anything. Okay, so no questions. I think I'll move on. Okay, so with that out of the way, what the hell is a GPT? What the hell is ChatGPT? So GPT stands for Generative Pre-trained Transformer. That's a mouthful. So what exactly is it, right? So it's a type of neural network architecture based on the transformer, and the transformer was a neural network architecture that was published in 2017 from Google. And the generative part in the name refers to what a GPT does. It generates text, right? We know that GPT generates text. Pre-trained references the fact that it's trained on a bunch of text from the internet, books, Wikipedia. And transformer, of course, is referencing the fact that the type of neural network architecture being used is a transformer. Now, what exactly does a GPT do? Like, how does it, we saw that in the previous example, classifying a digit, it has 10 outputs, classifying, like you're using your age, height, and shoe size to classify, how tall you are, or whatever. Those are all possible things. So what the hell does a GPT do? So a GPT performs what we call next word prediction or language modeling. And that is the task of predicting the next word in the sequence. So for example, if we're given the sequence, not all heroes wear capes, we train a GPT to predict the next word. So given just the word not, we want it to predict all. Given just the sentence not all, we want it to predict heroes. Given not all heroes, we want it to predict where, and then given not all heroes where, we give it capes, right? Now, we don't just do that with simple sentences. Instead, we show GPT an entire Wikipedia page, for example, right? So if you imagine that there are 1,000 words on a Wikipedia page, like 1,000 words in the document, well, then we can train it to make 999 predictions, right? You give it the first word, it predicts the second word. You give it the first and second word, it predicts the third. Of course, for the whole, like the very last word, capes, there's nothing to predict at the end. So that's why it's 999 and not 1,000. Now, we call this self-supervised learning because unlike the previous example I showed you of cats and dogs, you don't need human labelers, right? If you want to classify pictures of cats and dogs, you need to, pay a workforce of people to like sit down and label pictures of cats and dogs. You show them pictures of cats and dogs and they click a button saying, that's a cat, that's a dog, that's a cat, that's a dog. And you need it to be human labeled, and we call that supervised learning because it's being supervised by humans. Self-supervised learning is what we're doing with ChatGPT because, we don't need to label the data. If you give me a Wikipedia page, I already have the labels, right? It's in the text itself. And what this allows us to do is train GPTs on lots of data. This is a screenshot of a table in the GPT-3 paper where they show you how much data and what they actually trained it on. So here they're showing you they trained it on 300 billion tokens. You can kind of think of tokens like words. And you can see where they got the data from. Common crawl just means the internet, like you crawl the internet for data. Books 1 and books 2 is a data set of books, and Wikipedia is, well, Wikipedia. So yeah, you can train it basically on any raw text that you get, and it'll just learn to predict the next word. And of course, to show it lots of data and to have it learn from it, you also need a really big model. This is a graph of like how over time the models have gotten bigger. Nowadays, they're actually getting a little bit smaller. We've learned how to be more efficient with them. And we realize we don't actually need them that big. But GPT-3, for example, is 175 billion parameters, weights, right? The weights in our neural network. Remember, if we quickly go back to the neural network playground, right? For our very simple, two-layer 6 neuron network, if we count the number of parameters, right? 2 times 6 plus 6 times 6 plus 6 times 1, right? Because that's how you can count it by the number of connections. So it's like what? 2 times 6 plus 2 times 6 plus 6 times 1. Whoops. Plus 6 times 1. That's 30 parameters. This neural network has 30 parameters. That's it. GPT-3 has 175 billion. Yeah, that's a lot of parameters. If you assume that every parameter is a 16-bit floating point number saved, then that's 350 gigabytes of data. The model itself, just the weights. So yeah, when you scale the data and the model, as we saw in deep learning, you can unlock the ability of machine learning, and that's why we call them large language models, right? They're trained on lots of data and they have lots of parameters. But at the end of the day, they're just GPTs. They're just a GPT under the hood, just a simple neural network. Now, that does beg the question: if GPTs are just next word predictors, how do we produce full sentences, right? ChatGPT just doesn't give you one word answers. It gives you an entire sentence. So the way that works is we call that autoregressive decoding. And what that means is we start with some input sentence. So the prompt, right? Recite the first law in this case. And the model then predicts the word We then feed back into the model. Then we predict robot. Then we feed robot back into our input. And then we predict, what's the next? Then we predict may. And then we feed may back in. We predict not. And then we do that, right? In pseudocode, that essentially looks like this. For you do a loop for as many iterations as you want for the number of tokens you want to generate. You get the next word from the GPT model, and then you add it back into your input. That's it. That's what it means when we mean autoregressive. And the name autoregressive comes from regressive and auto. So regression, basically, you can kind of think of that as like predicting a future value. In this case, we're predicting the future word. And then auto means we're putting it back into the model. So that's where we get autoregressive. Okay, so that's all the background we need. Let's actually get to coding this thing. So in the chat, we're going to post a link to a Google Colab notebook, so you all can follow along. You can also just type this into your browser. I made a tiny URL link, and that should work. So I'm going to go ahead and click the link, and we're going to work from that. Now I'm going to give everybody a second to open up the Colab notebook. It should look like this. And I'll pause here for any questions people have so far before we move on. Oh, and I should also mention, you'll need a Google account if you want to run the code for this. You'll be able to look at it and follow along, of course, with my shared screen. But if you want to, if you also want to run the code yourself, you're going to need a Google account. Yeah. Cool. Is anyone having issues with opening the Colab, or can I kind of move on and get going?
No issues in the chat so far.
Yeah. Maybe somebody just give a quick thumbs up in the chat. Okay, thank you. All right. So again, let's go back to what the goal of this workshop is, right? So it's to understand partially, how the hell a GPT works, right? So we already covered a little bit of that. And remember, I'm basing this kind of workshop off a blog post I wrote called GPT in 60 Lines of NumPy. And we are going to be focusing on these last 15 lines of the code. By the way, this code's up on GitHub. GitHub is just a place where you upload source code. Yeah, so this part here, these 40 previous lines, that's the actual GPT neural network implementation. We're not going to be getting into that. It's beyond the scope of this workshop. I did write about it in my blog post, but we're just going to be focusing on this last part and deconstructing that. And also, of course, for that, we're going to need to use the rest of this code from my GitHub repo. So we're also going to be using that code. We're just going to be importing it, but not actually implementing it. Okay. So Google Colab, quick introduction. If you have never used Google Colab before, it's essentially like a Python environment in your browser that runs on some hosted computer on Google servers. So it doesn't run on your computer. It's connected to some other computer, and you can run Python code, right? So here I'm printing hello world, classic example. It's basically a Jupyter notebook. If any of you have used Jupyter in any of your classes. And if you've never used a Jupyter notebook before, the thing to know is the state persists between cells. So these are called code cells. You can hit the run button to run them, or you can also hit Shift Enter. And these are text cells, so they just hold text. And yeah, so the state persists between cells. So here I say x equals 10, and in the next one I can access x and print something out. Another thing you should know is that you actually don't need to type out print. The last line gets evaluated and printed out. So here I do x times -1, but it's only the last line that gets printed out. So if I do x times 2, you can see still only -10 gets printed out because only the last line gets printed. Okay, cool. Of course, it's Python, so you can also use lists. So here we're indexing a list. And remember, Python, we index from 0. So a at 1 is 4, right? Because this is a at 0, this is a at 1, this is a at 2. We can also do list comprehension. So here, by the way, if you've never used a list comprehension in Python, instead of like doing like a for loop, like a output equals array, and then for x in a, output dot append x times 2, right? Like this is how we would normally double a list, right? So here we get 2864 because we multiplied everything by 2. So instead of like doing like a for loop like this and typing append and using the append method, we can do it all in one line. And essentially what we do is we put our for loop on the right side here, and on the left side, we put what we want to put in the array. And this is just, a nice shorthand way to do things. And also it's actually faster. So if you have like a really long loop or something, it's actually a lot faster than using .append. Also, we should also know about dictionaries. If you've never used a dictionary in Python, it's basically like a key value lookup, like a table. So here we are saying we have the keys apple, banana, and pear, and apple is assigned a value of 10, banana 5, and pear -3. And so then when I do D at banana, it gives me 5, right? If I do D at pear, it'll give me -3. And if I do D at, let's say, grape, it'll actually say key error because it doesn't exist, right? Yeah. And then similar to list, there are also dictionary comprehensions. So here I'm iterating over my dictionary, d.items. I get the keys and the values, and then I'm just doubling the value. I'm saying, hey, put my key, but with my value, but have it multiplied by 2. And then finally, and the last thing about a Jupyter Notebook or Colab that you should know is we can use this -reset.f, and that will essentially clear all the variables so that they don't affect us later on. So here it says D is not defined, even though I did. So it's just a nice way to clear the state of the Colab notebook. Any questions? Okay, no questions. Okay, let's move on. Okay, so remember, we're going to be using the code from my blog, and the GitHub repo is called PicoGPT, by the way. So we're going to import that code so we can use it. So if we look at our Colab notebook right now, there's no files. So we're going to clone the repository, and then we can list. And then if I hit the refresh button here, we can see that we downloaded the repo, and then we can use all the code files from there now. So just as an example, we're going to import PicoGPT, and we're going to run the model. So we're going to run a GPT model and have it generate some text. So for example, Alan Turing theorized that computers would one day become. We're going to give the GPT model that prompt, and then we're going to say generate 8 tokens. And how big is the model going to be? 124 million parameters. Now, where are we getting the model from, by the way? I'm just going to run this and I'm going to talk about this in the background. We're getting the model from an open sourced, like where do we get the model weights from? Like who trained the model? OpenAI released GPT-2. So, ChatGPT, GPT-3 are all like their proprietary model. Like they didn't release the weights, but for GPT-2, which came out in 2018, I think, or 2019, they released the weights so that you can use them. And so that's what we're doing here. We're implementing a GPT and we're loading the GPT-2 weights and we're running the model. And so here you can see it generated Alan Turing theorized that computers would one day become the most powerful machines on the planet. Pretty cool. So again, going back to what we'll be coding, right? That was using this main function here. The main function calls the generate function and the generate function calls GPT-2. We're going to be re-implementing the main and the generate functions. But I wanted to show you what we'll be building up to. So that's what we'll essentially be coding, this main function. Okay, so let's actually get into it. Now, recall our original autoregressive loop from our presentation, this one over here. It looks like this, right? For I in range, or for underscore in range and tokens to generate, just get the next word and re-add it into our input. Now, this would suggest that this GPT function, right, that gives us the next word, takes as input a string and outputs the next word. Now, we saw earlier neural networks, they don't work with strings, they work with numbers. Everything needs to be a number. So in reality, that's not what the input signature for a GPT function looks like. It's a bit more complex than that. I simplified this, but this is a simplification. So what does a GPT function actually look like? So instead of having a string as input and a string as output, you have inputs, which is a array, a one-dimensional array with shape and seek. And what that means is that it has, we're saying that the length of that array is this value n seek. And then output is a 2D array of shape n seek, so it has n seek rows and n vocab columns. We'll get to what that means in a second, but just know that the input is a 1D array and the output is a 2D array of numbers. Okay, so what the hell does the input actually mean? What is the 1D array of? So instead of inputting some text, such as not all heroes wear capes, instead, what's inputted is a list of tokens represented by numbers. So for example, we break down not all heroes wear capes into the words dot, all heroes wear, and capes. So it's broken down into what we call tokens. In this case, our tokens are words. And what we do is we map them to numbers using some kind of vocabulary. So in this case, our vocabulary has a couple of words in them, all, not, heroes, the, where, dot, capes. And the way we map tokens to integers is we say, okay, not, where is that in our vocabulary? It's the first position, right? Because we index from 0, right? This is position 0, this is position 1, this is position 2. So therefore, our first token is 1, or token ID. We call it a token ID. The tokens are the actual strings. Our second one is 0 because vocab at 0 is all, right? And then so on, right? So we can actually see that. So we can, if we iterate through our IDs and then we print the vocabulary word, like that position in our vocabulary, we'll see we get our input sentence, right? Not all heroes wear capes. Does that make sense? Maybe somebody give me a thumbs up in the chat. Okay, I'm going to assume everyone understood. Okay, cool. Now, how did we get from text to tokens, right? We know how we get from tokens to inputs, right? We just use our vocab. But how the hell do we get from text to tokens? So this is what we call a tokenizer. And there are a bunch of different tokenizers out there. Okay, actually, I do have a question. I'm going to quickly answer this question. If we say they're stored as words, does that mean it could differentiate between hero and heroes? Doesn't know they're the same thing and doesn't know they're the same thing. Very, very good question. I'll answer that in a little bit later because it'll make a bit more sense later. Okay, so white space tokenizer. So how do we actually get from the text to tokens? So in this case, I implemented a very dumb tokenizer that takes our input and splits it by a space. So for example, if we use tokenizer.encode, it'll give us 1024, right? Because we initialized it with our vocabulary. And what's essentially happening is we're taking the text, we're splitting it, and then we're mapping it with our vocabulary. And then also we can go in the reverse direction, right? We can take our IDs here and we can convert them back into the text. Now, if we wanted to look at what the actual tokens are underneath, we could do that by using our vocabulary, right? For vocab at I for I and IDs. And we can see that the underlying tokens were not all heroes where. Now, what happens with our tokenizer if a word is encountered that's not in our vocabulary? Oops, we get an error. Shoes, right? Key error shoes, because shoes is not in our vocabulary. What about if there's multiple spaces? Well, that's a problem too, because we tokenize by space, we split by spaces, and now it's saying there's empty spaces in between the spaces, right? So that's not in our vocabulary either. What about punctuation? Well, that's another problem too, because now at the end, since we're splitting by space, well, that's a problem, right? Because now we have capes with an exclamation mark at the end. So this is just an example I gave, the whitespace tokenizer. In practice, we use way more complicated methods such as byte pair encoding and word piece. And they overcome these limitations and they're much more intelligent in the way they break things down. But the principle is essentially the same. We take a string, we break it down into smaller pieces called tokens, and then we use some kind of vocabulary to map those tokens to integers. Now, how do we decide what goes in our vocabulary? Well, tokenizers can be trained. So for example, byte pair encoding can be trained where you show it a bunch of text. Let's say you're like a dump of Wikipedia, and then it'll figure out intelligently what's the optimal vocabulary for your data. Okay, so to answer the question, how does it differentiate between hero and heroes? So it depends on the tokenizer. Some tokenizers will have a different entry for hero and heroes. Some tokenizers will have hero, and then it'll have just S as a token by itself, and it'll split hero into hero and S. And so it really just learns like S is like a pluralization of the previous word. But honestly, it's a machine learning algorithm. It's not that hard for it to learn hero and heroes. By the way, I spelled it wrong. I think like that. Yeah, like it's not that hard for it to figure out that both of those words like mean the same thing. It'll separately learn them because the data set will have both the word hero and heroes. Okay, so that was our input, right? So that's how we got our input from a string into a single one-dimensional array of integers. Now, I mentioned our output is a two-dimensional array of floating point numbers, right? Decimal numbers. What the hell does that mean? Okay, so it's a 2D array where output at I at j, right? So row I, column j, represents the model's predicted probability that the token vocab at j is the next token inputs at I plus 1. That's a bit complicated and a mouthful. So let's actually take a look. So let's say this is our example vocab and this is our example inputs, right? Not all heroes are capes. What this means is that outputs at 0, remember, outputs is a 2D array, so outputs at 0 is a one-dimensional array, right? Is going to be this list of numbers that maps to our vocabulary. So there's one number per item in our vocabulary, and it represents the probability that the next word is that word. So outputs at 0 means given just the word not, the model predicts the word all with the highest probability, right? 0.75 is assigned to all. Now output at 1 is, now we have two words. Given not all, the model predicts the word heroes with the highest probability, 0.8. And then obviously we can continue that for output at 2, output at 3. Now output at -1, AKA the last output, right? Because in Python, we can index an array by -1, right? So if I do inputs at -1, it'll give me, or I forgot to run this cell. If I do inputs at -1, it'll give me 4, right? So the last one would obviously represent, given the entire sequence, not all heroes where, the model predicts, in this case, capes with the highest probability. I just made these numbers up, by the way, but yeah. Now recall again, so now this makes sense now if we look back at the shape of our output. I think before I said the shape of our output is a 2D array where it has n seq columns, or sorry, n seq rows, and n vocab columns. So n seq is just the number of inputs here. So in this case, 4. And And vocab in this case is the number of things in our vocabulary. In this case, 1, 2, 3, 4, 5, 6, 7, right? So output at I is just the probability of the next word for that position. As an example, here's the array of things. Whoops, I think this has to be np.array. Ignore that. Whoops. Yeah, so this is just our simple 2D array. And if we want to get, for example, the next word, what the next word is, what we do is we take output at -1, because that's the probability of the next word on our entire sequence. And we simply take the position with the highest probability, right? So this is position 0, 1, 2, 3, 4, 5. Position 5 has the highest probability in this case, right? So, or sorry, position 6, I forgot to count one. So we could do that using this function np.argmax. And you can see it gives us 6, right? So np.argmax, so for example, in this case, I'll just show as an example, 1, 20, 100, 12. So position number 2, right here, that's the highest one. So np.argmax just gives us the highest in a specific list, right? And then of course, if we use our vocab to map it back, right, we can see it predicts capes. That's what it's doing. And now this is what we call greedy sampling or greedy decoding, where we have a probability distribution and we take the word with the highest probability as our prediction, because we're being greedy, right? We're like, oh, what's the highest value? Take that. There are other ways to do it. For example, you can directly sample from the distribution. So for example, instead of, picking capes, you can be like, with a 0.85% probability, pick capes. With a 0.05%, or sorry, 0.85 is 85%. So with an 85% probability, pick capes. With the 5% probability, pick a period. And then you can also get more fancy. You can add things like top P and top K sampling, which are like more complicated techniques where you can modify the distributions to get like different behaviors. But for our purposes, we're going to keep it simple. We're just going to be greedy and take the highest probability output, right? Yeah, and so with that gives us our new autoregressive loop that's more accurate now. And it looks like this. For I in range and tokens to generate, we get our output from the input IDs, and then we take the argmax of the last array, and that'll give us our next, token ID, and then we add that to our list of inputs. And then that's it. That's our autoregressive loop. Now, this does beg the question. We're only using output at -1, right? The very last one. Why isn't that a bit inefficient? What the hell are all the other ones for, right? Well, the purpose of those is during inference, like during like kind of this prediction phase. You're right. Like we don't need all the other ones. We only need output at -1. But when you're training the model, right? Ideally, we want it to, as we saw before with our language modeling slide here, right? We want it to predict all given just not. We want to predict heroes just given not all, right? We want it to do all those things. And we have those predictions, right? It outputs and seek different predictions. So it does that all at once in parallel, right? Because if it didn't do that, then what we'd have to do is if we had 100 words, we'd have to do 100 forward passes of the model to make all 100 predictions. But since it outputs 100 probability distributions in parallel, you only have to do one forward pass. And that's what makes the transformer, the underlying architecture of a GPT, really efficient at training. It can make all these predictions in parallel. And we can train it on like a lot of text at the same time. Okay, that was probably one of the harder parts to understand. Any questions about the output? Okay. If a question comes up, I'll address it, but now we're in kind of the home stretch. So we've covered the input and output. Let's actually get to, but we did this all in kind of an abstract way, using like my white space tokenizer, and I just came up with this output array. Let's actually get into what the actual stuff looks like. Now, let's load all the GPT-2 files. So here we're using the utils file from PicoGPT, right? PicoGPT/utils. And there's this function that will download and load the model weights of GPT-2, the tokenizer that GPT-2 uses, and also what we call hyperparameters, which is just some information about the model. So because we ran the main function before, it did download. Like we already downloaded it in the models directory here. We already have the downloaded files. But yeah, so now we've loaded the tokenizer, the hyperparameters, and the parameters. So let's look at the tokenizer first. Okay, so the tokenizer that GPT-2 uses is called byte pair encoding, the BPE tokenizer. And this is what it looks like, right? So not all hero wears capes gets tokenized to 3673, 477, etc. And then of course, we can go from the IDs back, and we can also look at what the actual tokens look like underneath. So confusingly, they called the vocabulary decoder, but if we use the vocabulary to look at what's underneath, we can see what's actually underneath. So here we can see not, that's our first token. All is our second token, and this little G is actually just a space. It's just helped. I don't know why they did this, but they used it to like help visualize things. And then you can see heroes, where, and then curiously, you can actually see capes is split into two parts, right? Cape, cape, and then ES for maybe plurality. This is just what the tokenizer came up with. And then of course we get our punctuation at the end, the dot. Yeah. And a nice thing about BPE is it can actually tokenize anything, right? So here, this is not a word. ZJQFL is not a word, but it'll basically, if it doesn't recognize something, it'll just break it down into smaller pieces that it does understand. So here, individual characters. Yeah. And finally, we can also look at how big our vocabulary is. How big is our vocabulary actually? Wow, that's huge. 50K words. So there are 50K, or sorry, I should say 50K tokens in our vocabulary for GPT-2. Okay, so what about H-params? What is H-params? So H-params is just a dictionary with a couple of bits and pieces of information. So N vocab, that's the size of our vocabulary we saw earlier, 50,000. N layer is the number of hidden layers in our neural network. In this case, GPT-2 has 12. N embed is the width, the number of neurons per layer. In this case, 678. NCTX is the context length. How many inputs, how many tokens can our model accept? Like how big can the input be? In this case, it's 1,000. ChatGPT, I think, is 8,000 tokens. And GPT-4, which just came out last week, I think can get up to 32,000. And finally, NHEAD. Don't worry too much about what that actually means. That's an implementation detail of the transformer. Just know it's something that it's just a hyperparameter that we can also set that kind of determines the architecture of the model. Okay, so that's H-params, hyperparameters. Now let's get to the actual weights, the parameters. So params, we loaded 3 things, right? Tokenizer, H-params, which is a dictionary, and params. Params is also a dictionary. In this case, it has 4 keys: blocks, LNF, WPE, and WTE. Don't worry about what those are. Those are just parameters of the model. In this case, blocks actually is each layer. So if I do len of params at blocks, you can actually see that there's 12, right? There's 12 things here for our 12 layers. The other ones are just like regular parameters. So if I print params at WTE, you can see it's just numbers, right? If we go back to our playground.tensorflow, right, we saw that the weights are just numbers: 0.25, 0.25, 0.25, negative 0.54, right? That's this part. That's what params is. It's just the numbers. And we can count how many parameters we have in total by going through our dictionary recursively and just counting how many parameters are in each array using this code here. And you can see 124 million, which makes sense because when we loaded our model, we asked it, give us 124 million. By the way, GPT-2 comes in a bunch of different sizes. Let me just quickly look. It comes in, they released a 124 million, 355 million, 774 million, and 1.5 billion. Remember, GPT-3 is 175 billion, much, much larger, and also trained on more data. But yeah, so yeah, that all checks out. Okay, so let's move on to the actual code that we want to get. So the first is we're not implementing the actual GPT architecture. That's going to be given to us. So let's import it from our Pico GPT repo. Remember, we are only implementing this last part, generate and main. But to implement generate, we need the model implementation. So we're going to import that. We're not going to implement that ourselves. Now, before, when we looked at our autoregressive loop, based on this, it would look like our function signature just takes a list of IDs, right? But actually, it's a bit more complicated than that. If we actually look at what the function signature looks like, you can see, in addition to inputs, the IDs, right, the token IDs, it also accepts our parameters that we saw earlier, WTE, WPE, blocks, LNF, and it also accepts the hyperparameter nhead. So given some input IDs, here are input IDs, we can call our GPT-2 function by passing our input IDs, giving it our parameters. If you've never seen this notation before, this double asterisk in Python, it means you're unpacking your dictionary into a function. So instead of having to explicitly write like WTE equals params at WTE, WPE equals params at WPE, and etc., you can use this shorthand asterisk params to unpack it into the function. And since the keys we saw earlier, the keys blocks, LNF, WP, WTE are already named correctly to the function, we can just do that. And then of course, nhead, we need to use our hparams dictionary to provide nhead. And we get our output. So we do a forward pass of our model, and we can see our output, remember, has shape nseq, in this case 8, right? 1, 2, 3, 4, 5, 6, 7, 8. And then the second dimension is n vocab, right? A probability distribution over your vocab, which in this case is 50K. Now, to get our prediction, we only want the last entry, right, for the entire sequence. And we do next ID, and we can see that it predicts tree. If we did it for, let's say, the second last entry for our sentence, the apple doesn't fall far from, we expect it to be from, right? In which case, oh, sorry. So we expect it to be the, right? Fall far from the, right? So you can see, actually, if I did 0 for the, it gets, let's actually do the apple. Let's do the apple is, right? So it predicts the apple is, which is understandable, because like, how is it supposed to know that the rest of the sentences doesn't fall far from the tree, right? If you're given just the apple, you wouldn't know what to predict next, right? So anyways, but to get our next ID for the entire sequence, we do the apple doesn't fall far from the, and we take the -1, the last output probability distribution. Okay, does that make sense? Any questions so far? Okay, so let's move on then. Okay, so that's all we need now. We have everything in place to actually finally re-implement those last 15 lines. So let's reset our variables. So we're starting from fresh, and let's actually implement it. So here we're going to import NumPy, which we were using before to get the argmax. TQDM is just a progress bar. I'll just quickly show you what it does. Like if I do from TQDM, import TQDM, if I just do like for I in range like 100, and let's actually just also import time. If I do like time.sleep at 1, right? So if I do this regularly, right, this for loop is running, but I can't check, I don't know where I am. If I wrap it around TQDM, it's just a nice little utility where you can now see a little progress bar as it's iterating through the loop. Yeah. Okay, so now GPT-2, that's our GPT-2 function we just used. And then of course the loading of the tokenizer params and whatnot. Okay, so here is our autoregressive loop, right? So we take as input our IDs, our parameters, and head, and the number of tokens we'd like to generate. And we do our little loop. We get the output, which we should call output, but I call it Rajas here, it's fine. We get our output here, and then we get the argmax to get the next ID, and then we append that back into our input, just as we did before, right? This is our autoregressive loop. And then finally, we only want to return the generated output, right? So inputs will at the end of the include both the actual input and what we generated. We only want to output, the stuff we generated. So we truncate our output by whatever like minus n tokens to generate to only get the stuff we generated. And then of course our main function, we load our parameters, we load our tokenizer, we load everything else. Well, I should probably say this is tokenizer. I forgot to change that. Yeah, so we load our tokenizer, h params and params. We then tokenize it. This line here is just to make sure that we're not exceeding the max context length, right? So here we're saying, what's our input length? Add the number of tokens we'd like to generate, make sure that's less than the capacity of the model. Then finally, we input everything into our generate function, and then we use our decode, or tokenizer.decode, to take all those IDs, map them back to text, and then we return that. So let's actually run our main function here. So again, we're going to use the same example we used in the intro. Alan Turing theorized that computers would one day become, generate 8 tokens, and use a model size of 124 million. So let's actually run it. And voila, boom, we get the most powerful machines on the planet. And that's pretty much it. I should mention one thing I did forget to say is, you'll notice if you actually print out output here, if we reload all of this, whoops. If we, oh shit, I think I have to go back here. Yeah, here. And if we go back here and look at our output exactly, like let's say you look at output at -1, you'll notice that it's not probabilities. I lied to you. They're not probabilities because they're actually raw scores. And like the example I showed you with the digits, these are before you turn them into probabilities. You can turn them into probabilities between 0 and 1, but it'll still hold that, the value that's the highest will still end up with the highest probability. So in this case, even if it's not probabilities, np.argmax will still give us the token with the highest number, which also happens to be the one with the highest probability. So that's why we don't actually need to convert them into probabilities, although there is a way to do that. But yeah. Anyways, but yeah, I think that's pretty much it. That's all I have for you guys today. And if you have any questions, do let me know. But that was kind of an introduction to GPT. For next steps, in the Colab notebook, and the slides, I linked my original blog post. And that blog post goes through a lot more content. It actually goes through the architecture, it goes through training, it goes through other stuff, next steps, resources, how to make it fast, what's instruction fine-tuning. It goes into a bunch of different topics. But for now, I think that's a pretty good surface level of how GPTs work, and I hope you got something out of that. Yeah, thank you. So I have a question here from Omar. Would you use something like the softmax function for conversion? Exactly. That's correct. You'd use the softmax function. The reason why we don't need to is because softmax is monotonic. Is a monotonic function. So monotonic function. It basically means that even after you apply the function, the order of things is preserved. So the highest value will always stay the highest. The lowest value will always stay the lowest. So you don't need to convert it to probabilities, but you can if you want. Actually, there's a thing. If you wanted to directly sample from the probability distribution, I think I mentioned before, we were using greedy decoding, where we take the highest probability value. If you wanted to instead use something like top K or top P, where you sample directly from the probability distribution, then yeah, you would need to convert them to probabilities first. Okay, cool question. So how is training LLMs different from other kinds of training other kinds of neural networks? So jkmodi.com. So there is a part here where I talk about training in the blog post. I mean, there's 2 parts actually. So it is like training any other neural network. You just use gradient descent with respect to some loss function. In fact, you use the same loss function that you use for like a CNN for classification. If you're familiar, you'll know it as the cross entropy loss. And you just do the cross entropy loss. That's pretty much it. And then it's a pretty standard set of tricks, right? You use the same tricks that you use for a CNN. You use the atom optimizer, like here. I think I wrote about it here. Like you'd want to use the standard set of tricks, like using the atom optimizer, finding the optimal learning rate, regularization, using either dropout or weight decay or something like that. I mean, I think transformers specifically are highly sensitive to learning rate in my experience. So there's that extra element to it, but it's pretty standard training compared to other networks. The main kind of issue with training a GPT is the scale we do it at. No other models are, 175 billion parameters, like stable diffusion, Midjourney, and all those generative AI, like image models are like, less than 10 billion. So when you're training something at the scale of like 175 billion, there's a lot of work that goes into engineering, code that works like that. GPT in 60 lines is great, but in reality, like you're looking at like, you're looking at like code bases like Megatron LM. Like it's huge code base just to train a model at this scale, right? This is NVIDIA's training framework for their GPT models. It's huge. There's so much involved. It's very complex. And this is, this is the life's work of so many people, right? Their PhDs are in distributed training and neural network, like training neural networks at this scale. So yeah, the main thing is just the scale. Is the progress on large language models exponential, or has it plateaued for a while? I don't know how to answer that question. Like performance, performance. I don't like but like there's no metric. I guess there's no one metric. In my experience, it's been quite moonshot. Like where we were like in 2017, 2018 with large language models. I mean, we didn't even call them large language models because they weren't capable of any of that stuff. Like they've gotten a lot better. Like in my experience, like in my opinion, like large language models are the first like step towards AGIs that I've ever seen. Like you can actually play GPT-4, like ChatGPT in chess, and it can play chess. Like even though it wasn't explicitly trained to do so, just by absorbing information on the internet. I mean, I don't know that they could have potentially like added that to the training data set, but even then it's still fascinating that you have one model that can play chess, give you suggestions on birthday ideas that you can have a conversation with, that you can kind of, instead of using Google search, you can just ask it questions about whatever you want, right? It's quite fascinating. So I'd say it's been pretty big, like pretty great progress, and it's kind of hard to tell like where we'll be in the future. These things develop so rapidly. We'll have to see. Any other questions? Okay.
Any questions? No.
Oh, we got one more. I heard that RL, reinforcement learning, is sometimes used in the training for LLMs like ChatGPT. So the paper I'll point you to there is Instruct GPT. This is the paper that you want to read up on that. Basically, the idea here is you get humans, you basically train a model, or you train the model using a reinforcement learning objective that optimizes preference. So you show people a bunch of like here's 4 outputs from different models. Which one's the best one? And they click it, and then you optimize like a reinforcement learning network to figure out how preferences are used, and then you can basically train the model like that. It's still quite new. Like this is very novel research. Like literally not even that long ago. And it's kind of being just like research right now. But this is the kind of status quo right now is like GPT-4 and all the latest language models are using some kind of what we call RLHF, reinforcement learning from human feedback. Yeah, so there is that element to it too. what would you recommend to a student who started machine learning to get hands-on experience and build their career in data science and AI? That's an excellent question. Honestly, the hardest part to like getting involved in AI, machine learning, neural networks, and all that is just doing anything. Like, don't get too caught up in like, oh, should I do this course, or like what's hot right now? Like, should I learn like, you know, like what technology should I learn? Should I learn TensorFlow? Should I learn this or should I learn that? Like, there's no right answer. And I'd say the mindset to have is just do anything. Like pick any course, any project, anything, and just go. Right. Because right now, like, if you're just getting into the space, like it's can be overwhelming. There's so many things to learn that you end up learning nothing because you don't know where to start. My suggestion would be just start somewhere. A good place to start would just be like Coursera machine learning. There's a great Coursera course on machine learning from Andrew Ng. It's a classic, right? Like you can just start with that and kind of go from there, right? I also really like CS231N from Stanford. They have some really great course notes, and they have also great assignments that you can do as well. And just get to kind of get into things because machine learning and deep learning is like a huge field. There's like so much to learn that you just get an advantage if you just start and you start cranking away at things. Like things progress so quickly. There's so many research papers coming out that keeping up with it can be a lot. And so just getting your foot in and just starting with anything is what I'd recommend. Don't get too caught up on like all the courses and what to do and all that. Yeah, and also McMaster offers a DataSci 3ML3, which goes through the basics of neural networks and machine learning techniques. Thanks for the shout out, Omar. I gave the foundations, but I don't know how to get involved in business in AI. I don't know how to get involved doing business in AI. What do you mean by like business? I guess like a business. I mean, honestly, that's a tough question. I definitely am more on like the technical side of things. I mean, with anything with business, it's kind of just like, where's the demand for stuff, right? Like right now, like as an example, the first two immediate kind of use cases for large language models that appeared, first was copywriting. You look at companies and startups like Jasper AI, which are raised millions of dollars, that basically use like ChatGPT or like GPT-3 and stuff to like do copywriting for writers, and product descriptions and all that kind of stuff. That was kind of like the first use case people saw. And like now I think a big one is like education. I mean, if you look at GPT-4 paper, and you scroll down to their images section, GPT-4 also supports images now. You can see that like, here's like a physics problem in French, not even in English, in French. And they show it to the model and they ask it, answer question 1A, think step by step. And here's your solution that it gave. So immediately to me, like there's definitely going to be tons of applications in education. If anything, the way education will be done is shaked, it shake forever. Like if ChatGPT can do your homework, how do you work around that, right? So I think that's a good way to like start thinking about the business side of things, like how is life affected, and where are there going to be new opportunities to use this technology. And again, that doesn't require you to be technical. You don't need to know how ChatGPT works to use it for your business, right? You just need to know how to use their platform. That's it. McMaster EcoCars team is doing machine learning related stuff for self-driving perception. There are other clubs that do related stuff as well. McMaster Autoplow also comes to mind. Yeah, so you can also get involved in clubs. There's also the McMaster AI Society. that also like work on this kind of stuff. So yeah.
There's no questions like what we can make up.
Awesome. Okay. Yeah, thank you for everyone for coming out. I hope you took something out of this presentation, and yeah, I think we'll end it there.
Thank you so much.